There it goes. Oh, beautiful. All right, good afternoon, everyone. Welcome to the first of what I hope will be very many Ham Science Thursday afternoon Zoom calls. As everyone I think knows, our main goal for the next few months or a year or however long it takes is to work on our data analysis and our findings from the past couple of eclipses and all the other interesting ionospheric phenomena that happens on a daily and nightly basis. So that's why we've got a lot of folks here representing the science community along with all of us citizen scientists. So we're one big happy family, as they say. Um, I think we'll get right into it today. The only one comment I want to make of maybe general interest to the group is I've been sitting back the last couple of days and thinking through all the Festival of Eclipse Ionospheric Science events. It seems like we've got a lot of people who've helped create a lot of data, and it's a lot of different places. You know, we've got the medium wave recording stuff in one place and the reverse beacon net spot somewhere else, and we've got so on and so forth. It's kind of scattered. So I think I'm going to try and make a chart and just kind of have a collective view of where kind of sort of everything is. I don't need a tremendous amount of detail, but I think the eventual goal is to get most of this stuff moved to a place like Zenodo. So it's secured, it's publicly accessible, and that'll it just because it's the right thing to do and that meets the terms of our grants and so on and so forth. But we don't really know what we've got, I think, until we all write it down. And hopefully in the next couple of weeks, I'll work on that and you all can help as I present it here and help me fill in the gaps. So hopefully that seems like a reasonable idea to everyone. I think I'll get right into the program today. Welcome to everyone who's participating. Mostly familiar faces, but a few new ones. So welcome. Hopefully a little blurb about our scientific method presentation today encouraged a few people to join. So Mary Lou West, if you'd like to take it away, Mary Lou, we can start your PowerPoint and begin our educational experience.
Okay, so I'm going to share my screen. Okay, so you should see the scientific method. Everybody got that? Okay, so I know we have a lot of very different backgrounds for the people in this group. So this is going to be starting fairly low key. This is the sort of thing I would give to sophomores in the physics program at Montclair State when we were about to start individual projects of some sort. But this is just the very beginning. I'll give you more meat on the bones next week. So anyway, a little bit about what is the scientific method. Okay. So the first question is, what are our questions? What sort of things should we be investigating? So I want everybody, this is a very interactive sort of thing. I want everybody to have a pencil and paper in front of them and to write down some things when I ask you to. So one, write down some ham science questions that we want to investigate. Go.
Hi, I'm on my second Zoom.
Okay. So is everybody writing down a science question that we in this group want to investigate?
Recording in progress.
Good to know.
Good to know.
Okay, so let's see what
There are a bunch of people who aren't muted.
evidently. Okay, so everybody can unmute themselves at this point if they want. I want to.
You just muted yourself, Mary Lou.
I think we got globally muted.
Yeah, you'll need to unmute yourself, Mary Lou.
There we go. Is that okay now? Can you hear me?
Yes.
Okay.
Yep.
Thank you. I can see Bill. So what sort of questions have people written down? So David McGaw, what'd you write down?
First, measure the height of the ionospheric layers, and
Hey,
in particular,
stop right there. You only get one thing. Height of ionosphere.
oh, you didn't tell me that.
You got another better one you want to say? Go ahead.
Well, closer to the heart is monitor sporadic E openings.
Ah, that's a good one. So who's got something else? Mackenzie, what'd you write down?
I wrote down, how is the ionosphere affected by the solar eclipse?
Oh, you got a big one there. Yeah, that's a good one. Ron, what'd you write down?
Does the eclipse's effect on the ionosphere vary from geographic locations on the Earth? In other words,
Ooh.
is the effect of the eclipse in the ionosphere different in Brazil than Easter Island as opposed to Canada?
I think we all should go to Easter Island and check that out, right? John Lanigan's going to go there. Right. Okay. So who else has got another one? Let's see. Bill, what do you think?
I wrote down impact of coronal mass ejections on the ionosphere.
That's a great one. Yeah. We would certainly like to know what the coronal mass ejections do to the ionosphere. So sideways from that one, a couple nights ago, I heard two scientists from the Naval Research Lab talk about coronal mass ejections and how they're getting machinery to put on a new spacecraft that's going to go and check it all out. So might have some friends there. Anybody else?
That was a really good presentation, Mary Lou. My wife and I enjoyed it.
Did you enjoy it? Yeah, I thought that was good too. I liked Arnaud, the Frenchman. He was
Yes.
very cool. So they're building a new kind of coronagraph to put on one of the GOES satellites that will look, be parked at what, the L1 position and look at the sun all the time and warn us about stuff that's coming. Okay, anybody else got a good one? I can't see you all.
How about this one?
This one might be challenging. What is the mechanism behind gray line propagation effects?
Oh yeah. Yeah, we don't, that's really weird, isn't it, gray line? Why does it do that? Really part of that is, does the solar eclipse do the same thing as the gray line, but only quicker? We don't really know.
Mine was very similar, except focusing above 20 megahertz.
You mean a frequency above 20 megahertz?
Correct.
Yeah, okay. Well, don't know. So a lot of, just to say, one of the things that I had trouble with students when I was teaching, I taught for 42 years. And it always annoyed me that the graduate students who, having just graduated in physics somewhere else, thought that they now knew everything, right? This is not necessarily true at all. But I would ask a question and they'd start explaining it to somebody and they would drift off into total nonsense. And I would say, you're really spinning here. You don't really know about that. And they said, well, yeah, but I wanted to impress them. No, you have to learn to say, I don't know. And so every week when we would meet, after a while, it became clear we had to practice at the beginning of the weekly meeting all together saying, I don't know. So that they could actually get it out of their little mouths and be able to say to somebody, I don't know about that. Because by the time you get a PhD, you say it all the time. So, but that was always funny to me. Okay, so we got all sorts of ideas. So let's proceed here. So everybody's written down some questions. And we have those done. So here's the ones we're especially tasked to do. Oh, come on. So this came from the HAMSI website. We have got grants that say we're to investigate how does the ionosphere couple with the neutral atmosphere and with space? How does the ionosphere respond to inputs from space and from the neutral atmosphere? How do solar eclipses impact the ionospheric structure and dynamics? So there we have two things, the structure, the static structure, but then the dynamic activity. How does it make it do something? How does energy move from the lower atmosphere to the upper atmosphere to generate TIDs, traveling ionospheric disturbances? So this is my particular task that Nathaniel has given to me. And it's certainly not at all clear how anything gets from the lower atmosphere, which is where we're living right now, so sea level or thereabouts. So I live in New Jersey, and we're at, I think here, 200 feet above sea level. Good wave would get us. Anyhow, all the way up to the upper atmosphere and then up into the ionosphere. Now, what percentage of observed TIDs, these are traveling ionospheric disturbances, correlate with geomagnetic activity, which is something different? I got statistics, but they're not helping. How do solar flares and geomagnetic storms affect ionospheric dynamics and high frequency radio communications? And here's the what drives the whole thing. It's communications. How do any of these things make communications have blackouts or come and go or fade in or out? And so these are the things we especially are supposed to do. And there's a lot of good stuff that you mentioned that we will do along the way as well. Okay. We need to measure or to find a proxy to measure. Yeah, go ahead.
Excuse me, Mary Lou.
Yes.
Nick here. Getting
Hi,
back
Nick.
to the last list there, like how do solar flares and geomagnetic storms affect ionospheric dynamics and HF radio communications? Now, this is not a new question. So
none of these are new questions.
No, exactly. So at what point, like maybe you're just going to tell me this in a minute, but the first thing that I tend to do with something like that is say, well, I don't know, as you say, and well, what have other people done in the past, sort of to try and answer this question. So is that part of it, or are we starting from ground zero?
No. A lot of this is go read the past and see what people found.
Okay.
Yes.
All right.
Yes.
I'll stand back then.
Okay. Indeed, our ancestors have done all sorts of wonderful things, and we should read the things that our ancestors have told to us, and that's always a good place to start. Indeed. Thank you for your comment there. So we need to measure a bunch of different things in many different ways, and sometimes they're hard to measure, so you find some proxy or something that will stand in for the measurement, and you use that and hope that it works. But anyway, we need to measure radio signals, of course, the radio frequencies that they're at. Time is very important. Distance, separations between stations, for instance, is often very important. The height of the ionosphere, which you measure vertically rather than horizontally, that's very important. And that was one of the questions indeed. We want to measure Doppler shifts, which have to do with dynamics and moving. Then there's the solar flares and coronal mass ejections, which the sun does it in its own little time scale, and we have to keep track of those. And then, of course, geomagnetic storms that come from that sort of thing. Well, what are their units? So here's the units for some of these. So with radio signals, you can measure or write down, is there one or not? Yes or no. It's a binary sort of thing. I got one today and I didn't get one yesterday. What was the strength of the signal? If you did get one, was it weak or was it a very strong signal? Radio frequency is measured in hertz, which is cycles per second. Time is measured in seconds. Distance separations between stations we measure now in kilometers. Latitude and longitude, which is what Ron was interested in, is measured in degrees. So up and down from the equator and roundabout from Greenwich. But does this really have an effect? Sure it does. How much of an effect? Well, depends. Doppler shifts, which are measured in hertz, velocity, which we measure in meters per second, or in my car, miles per hour. Mass we haven't mentioned here, but that comes into CMEs. We measure in kilograms. Magnetic field strength, many people don't know what that is measured in, but it's measured in Teslas, or in the Earth's case, nanoteslas, because it's pretty small, and energy, of course, in joules. So analysis tools, here we go. What do we have that can be of easy use for understanding or making an explanation for many of these things we've measured? There's a wonderful power of numbers. We can say a lot in words, but numbers are amazingly powerful. And here, Nick should bow down in front of our ancestors. Our ancestors from the times of the ancient Babylonians and Greeks and whatnot have done wonderful things to teach us how to deal with numbers in many wonderful and sometimes non-intuitive ways. We have a lot of techniques we can borrow from statistics or calculus or any number of things to deal with numbers. And I'm now in a group which is up to Fourier transforms. Oh, Lordy. But they are a very powerful way to deal with numbers. Then there's the power of graphs. Many of us are visual learners rather than audio or just reading, and really can get a lot more understanding if you have a graph, which is an X and a Y axis and some wiggly line that goes up between them somehow. I really like graphs. Anyway, then there's the power of touching objects. I think that physical intuition is acquired through direct experience. A person has to hold an object, has to play with it, has to move with it, has to feel the force in their own hands between two objects to really understand the physical universe. And I have discussions with people who don't think that's necessary, but I think it really is, even up to building circuits and trying to imagining how electrons are going to run through this bunch of wires and chips and whatnot. So I have a little story about that. Did any of you see the movie Oppenheimer this summer?
Oh, for sure, yes.
I thought it was a good movie. So I'm old enough that I knew some of the people in the movie who are played by the actors in the movie, rather. And one of them was a professor at Columbia when I was there for graduate work, and that was I. Rabi. Does anybody remember seeing him? He was the sort of shorter, chubby guy who talked to Robert Oppenheimer a lot. At any rate, two stories about Oppenheimer, about Rabi, is that one, he was being interviewed one day by a reporter who asked how he had gotten into physics, what had made him decide to do that as a career. And I love his reply. He said, well, he said, my mother, your mother, what about that? He said, well, my mother asked me a different question from all the other mothers after school. So when I come home from school, most of the mothers of my friends would say, did you learn anything in school today? And the kid would, yeah, I learned this or that. He said, my mother never said that. My mother said, did you ask any good questions today? So he said, what could I be but a physicist? So there you are. I thought that was great. But anyway, so one of our tasks really is to ask the good questions, and then the answers will flow from those. The other thing is, which bears on this question of physical intuition, Rabi's specialty was the movement of electrons through materials, mostly solid materials of various sorts, molecules of things. And he had a tremendous feeling or empathy for electrons. And you could ask him, if you put an electron over here next to this molecule, where would it go? And he could tell you. He'd think about it for a while and then he'd say, well, it would do that. And then somebody would do the experiment And by gum, the electron would do that exactly. So that was one of his great superpowers, was understanding electrons really, really well. Okay, so and then the last of our analysis tools that I've listed here is the power of writing it down. This was another problem I had with students at the college level, and also with adults older than that, is that people are loath to write stuff down. So with students, they would say, well, why should I bother writing this particular thing down? I'm the only one that's doing this experiment. I will remember what I did. Nobody else is ever going to need this. They will never do it. And I say, you're not, in this case, writing it down for somebody else. You're writing it down for yourself. Oh, I'll remember. Ha, 3 months later, why'd you do that? Huh, I don't remember. You didn't write it down, did you? And then I have this problem also with coders who don't comment their code. If you're making any sort of choice, write down why you made that choice. And then later, you, or in fact, somebody else, might indeed need that information. So a little story about that. Part of my PhD thesis involved a large simulation of motions within a galaxy. And I had inherited that from Edding, who had left, got his PhD and left. Nobody knew quite where he went, but English was not his native language. And so for this particular program, which was like 500 lines long, he had chosen variable names which did not sound like things in English. So mass was not mass. It was not even starting with an M. It was in some Asian language, more or less, and he had disappeared. I had a hard time figuring out what it was he meant by these things. It would have been really nice if he'd said, this stands for mass. Great. At any rate, write stuff down. That's why I made you write a piece of paper and a pencil today. I want you guys to write stuff down. Okay, next. So I really want to talk to you a little bit today about the scientific method, which probably you heard about in middle school or something like that. So I want you to take your piece of paper and your pencil and write down 5 things. First, what is the purpose of the scientific method? What does this method do for us? All right, and then write down 4 steps in this method. Go. Okay, let's see what we got here. John, good to see you again. Thanks for the tour of your lab. That was really,
you're welcome. We still have a half unfinished bag of popcorn to deal with.
Oh, I could have helped you out with that. Yes, the popcorn was fine. It was good to share a bag of popcorn with you. That was good. So what is the purpose of the scientific method? What'd you write down?
Allows for systematic observation methodology to I basically allows for a systematic observation method.
Okay, that's a good half of it. Come on, what do you write down? You have
That is
done,
written down. And you want the 4 steps?
no, we want somebody else to do that.
Oh, okay. I'm sorry.
Bill, what'd you write down for the 4 steps?
For the 4 steps, it's been a long time since I did the scientific method.
That's okay. Make them up. What'd you got? Say one
Okay,
thing. Say one thing.
First, develop a thesis or for something that happens.
Okay, that's great. Who's got a second step? Let's see.
I do.
Who said that? Whoever, just go ahead.
Then experiment.
Yes, yes. So one of the great things about the scientific method is it involves doing an experiment, which is really tough in astronomy, which is my field, because you can't go out there and whap the stars around and make them do stuff. So we have to be very clever and sneaky about it. All right, has anybody got another step?
Mary Lou?
Hypothesis.
So hypothesis really goes with the first step, which is make a thesis, an idea, something like that. Cool word. Okay, hang on. So what do we got?
Lou?
Yes.
So I'm not sure where this would fit in. I'm not really that sure about the scientific method, but I thought somewhere along the line you're going to want to ask a question or come up with a question, maybe towards the beginning. And I could be way out in left field, but that was something.
No, that's a good one too. Has anybody got some of the further steps? We got the first 2, which is ask a question and make a thesis and then do an experiment.
Research.
I was thinking of maybe just the first observation of a phenomena that leads to that question.
Analyze. Analyze.
Analyze. There's a good one. What the heck does that mean?
What happened and why?
Yeah, the why is the big part, right? Okay. Nobody's got the last one yet. Nobody ever gets the last one. Oh, shucks.
Sharing results.
Publish?
Yes, publish. Share results. So it doesn't really count if it's only in your head and your notebooks and you die unknown and unsupported and whatnot. You have to tell other people about it. All right, so here's what I wrote down. See if you like any of these at all. So the purpose to explain some small part of the universe. And for students that I had for many years, that was often one of the hardest things, to narrow your focus down to something small enough that you had a chance in one semester to explain it in any way. All right, so but we have a lot of people in this group and we have a lot of ideas. We can kind of dice it up later. So make an educated guess for an explanation. This is the one where you have some sort of a prior experience in life. You make a hypothesis, you have a theory, you have a model in your head of this is related to that. And that is what you start with the first time around. I think that CMEs are related to blackouts or whatever, something like that. Then part 2, you do an experiment. You decide something that you're going to physically do. You're going to observe something. You try to control all the variables except one of them. That's often a very difficult thing to do, especially if you're in like things with the ionosphere and things with astronomy. You cannot control the variables. Nature does that. You have to pick and choose from the things that you see go by, which ones have more or less the same variables. And then you write down numbers with units on them. So I'm very keen on writing units after numbers, which students were not keen on doing. They'd write down 57. And I'd say 57 watts. And they'd say, oh, you know, things. I said, no, I don't know things. Tell me what the units were. So I exhort you to do that as well. Number 3, this is the one under analysis or ask why. Compare experimental results that you just got to your theory. So you compare number 2 to number 1. And you think, well, what did it do? What did it get right? What did it get wrong? And you have to revise it. You have to revise your theory. You cannot revise the experiment. You can revise your theory. And one of the good ways to proceed then is to predict a new value. Well, if we made this a little bigger, then it should come out over here a little bigger, don't you think? Well, let's try it. And then you repeat steps 2 and 3 several times around, sometimes many times around. And finally, you get something where you think you really have got the experiment to be predicted well by the theory. You really think you got a handle on why how this works and everything. And then you tell about it. You tell about your best or final theory, you publish it, you tell other people. So in our society, it really is important that you tell other people about it. So we're going to try to do that. So types of theories and models and hypotheses and other words like that are there are four ways to state a theory, and you should be able to do at least 3 of them. If you're really lucky, the 4th one. And so I found that working with students, they often had a hard time with one or the other of these first 3, and they had to be trained and forced to do it in all cases. So you have a sentence in words. This is related to that, and usually it's a little better than that. When this goes up, that will go up as well, numerically. Then you make a graph, and you have an XY axis, and you write down numbers here, and you put units on them, and you write down numbers here, and you put units on them. And then you draw the pairs of numbers, and you connect them up with a line. And so when this one goes up, that one goes up as well. Now you have a sense of how much it goes up. Or in the very beginning, the first time you come to this step, you often generally don't have a good numerical sense for it. You draw the graph, and you just draw a line that goes up. That's a good first start. So besides having a sentence in English and a graph on paper, then you have a table of numbers. And this is often experimental results. And you have a column of X numbers, you have a column of Y numbers. By the end of another 5 minutes, you're going to have a column of 2 columns of numbers, and we'll see what happens there. And then if you're really, really lucky, you can get an equation that expresses in analytic form what that form of the graph is. That's the tough one. Newton did that real well, not the rest of us. So here's Mary Oliver's version. Mary Oliver's a poet from Ohio. Yay, Ohio, Gary. She was east of Cleveland. She's dead now, but I like to read her poetry. And she had the philosophy of life. This is what you were supposed to do every day, if at all possible. Pay attention. Look around, see what's happening in the world. Be amazed at something. I'm amazed at least once a day. Tell somebody about it, usually at dinner, right? There we go, Ed. So pay attention, be amazed, and tell about it. And that's the scientific method. Their start. Okay, so we're going to look a little bit at this particular graph, which was on the internet, yay, yesterday even. This is the one that came from Christina Collins and the grapes. Yay, John, look at this. And it's, so did everybody see this one?
Yep.
Okay, so we're going to look at this in some detail. It's labeled solar eclipse Doppler shift. And so the first thing to do when you get a graph is you look at the axes and see what their units are and what's going on. So on the bottom, we have numbers 13, 14, 15, 16, 17, and underneath it's written UTC hour. So this is evidently only one day. It doesn't somewhere on here have a date. I think I cut the date off. Sorry about that. Originally had a date, so 8 April 2024. And this is one day, not even the whole of the day. So the second half of the day in universal time coordinated. So time goes across here. Then we look at the left axis, the y-axis going up vertically, and it is written Doppler shift hertz. Oh, there's where the data is. And its numbers are -1.5, -1, -0.50, 0.51, and 1.5. All right. So this measures Doppler shift in hertz. And evidently from all the writing on this paper behind the graph, there were a whole bunch of people involved in this, and most of them were observing at, what frequency were they observing at?
10 megahertz.
10 megahertz. But two of them were kind of
There's a
sideways. And
15.
15 megahertz. What's with them? Oh, right. I'm glad to know that they were there as well. And then these people were in different places. Can anybody read the places in the back of the graph?
Mainly northeast.
Yes, so there's Harvard, Massachusetts, Groton, Massachusetts, Pepperell, Massachusetts, Harvard, Massachusetts, Vero Beach, Florida. Alrighty. Hampstead, North Carolina. So mostly Massachusetts, but we got some Florida and North Carolina folks in there as well. So it's
There's a
not
British
all one.
Columbia.
West Coast, yeah.
Oh yeah, British Columbia. Yes, Labby Smith. I don't know.
Ladysmith.
Ladysmith, British Columbia. All right, never been there. Should go there. Road trip. Anyway, so this is what we have, and what we want to do now is to interpret this graph. So I want to be able to say this is a graph of an experiment. It's more complicated than it, things just generally go up. So we would like to say a sentence, say two sentences, in fact, about what's going on in this graph. Who wants to try that?
Okay.
Nick, what do you got?
Here? Yeah. Well, I mean, obviously, like what's happening is that there's a frequency shift for many of them, but not all of them. Sort of first of all, the frequency goes down and then the frequency goes up again after a certain period of time. But the thing is that I am in British Columbia myself, and well.
Oh, is this you? Is this your data here?
No, it's not mine.
Oh,
no, it's actually, and I don't think I've met the person either. I talked to somebody at the workshop who knew the person, I think. But anyway.
Oh wow, you got to meet him because they're on this graph.
Yeah, but the thing is that like the British Columbia data is the one that's not following the rest of them, which to me makes some sense. But the thing is that although at first glance it looks like everybody's doing the same thing, they in fact aren't.
Right. So maybe next week you could look into that and find out what their excuse is.
Well, I think I know. Well, no, I don't think I
Okay,
know. I think I have a good guess.
Okay, don't tell us now.
Yeah.
But next week you're gonna tell.
Okay, I'll back off.
The British Columbia person. All right. Because I think we have enough to do to just get through this today. So very good. So I wanted somebody to say both of those things, or at least one of them. So you said one of them, but I would like to say the other one as well. Generally in this graph, and you're missing, of course, the whole extent of it. There was lots more graph beforehand, but the thing is, there is a general decline. There is a trend going downwards from 13 to 24. Do you see the general slope? And then on the slope, there's this big S-shaped thing which goes down and up and comes back. So there's two things here. There's the trend, which is gentle downwards, and then this big excursion which goes down and up. And many people evidently found the same sort of S-shaped curve as the others. All right, so now we need to get a little more numerical. What is the height or the depth? What is the largest extent of the S-shaped curve? I like to look at the positive part first. We see that they don't agree in time. There's a little bit of chicky moving to the right. But three of them at least go up to what level? Can anybody read that on the graph?
1.0.
1 hertz.
1.0. I love 1.0. Such a nice number. You can multiply by it and everything. So, we'll look at the next page, which is how to read such a graph. So this is just the Doppler shift. We've talked about the axes and what their values were, the meaning of each. One is time in one day, one is Doppler shift. We're not quite sure what Doppler shift means at this point, or at least some of us are not quite sure about that. We wanted to talk the trend, so I wanted you to say that there is this downward trend as you go through the day, and then there's this big S-shaped event, which is superimposed on that. So those are all statements in words. We read some numeric values, and now we want to check for reasonableness. And that's because not all of us are acquainted with reading Doppler shift graphs on a daily basis. What does this really mean? So I'm going to use the value, the top value there. So the Doppler shift values go from what through what to what? So Nick, say the values. What's the largest negative value?
I think the largest negative value is -1, but it was 0.0. But the thing is that I can't see it anymore. So
well, there is that. That's why I like to print things out and have a piece of paper here on the desk beside.
yeah, that's
anyway,
true. Actually,
so
I think I do have that page open.
It was like -1.1.
Yeah.
Yes, and then it goes through something up to 1.0. All right, so here's what I wanted you to say. It goes from -1 hertz through 0 to +1 hertz. Nobody said the units. So what what speed does this mean? Yeah, Nick, you're going to say something.
Sorry, no, I'll back off.
You didn't back it off, muttering to yourself. Okay, so what speed does this mean? Doppler shift means a speed, and the velocity or speed is the equation is the change in frequency divided by the frequency. So that's just a percentage because the frequency drops out. You divide frequency divided by frequency is 1, and so we don't care. So it's the change in frequency divided by the frequency, and all of that is multiplied by the speed of the wave. How fast does the speed of a radio wave go at?
Speed of light.
Speed of light, yay! So that's equal to the change in frequency goes from 0 to 1 hertz, or 0 to -1 hertz. The speed of light is 3 times 10 to the 8th meters per second. Whoopity-doo, fast. And then we divide by the frequency, and most of these was 10 megahertz. That's why I wrote that down. So mega is 6. 6 and another 10 makes 7. 10 to the 8th, take it divided by 10 to the 7th, gets you only a single 10. And 3 times a single 10 is called 30. So the resulting velocity from this graph goes from 0 up to 30 meters per second. How much is that? I don't really know. I grew up in the olden days when we didn't use the metric system. And 30 meters per second sounds like pretty fast. I could only jump maybe 1 meter every second. So 1 meter per second is a sort of running speed. I don't know, 30, faster than running. That doesn't mean much to me. So we're going to do it for reasonableness in my units, which is in my car, the miles per hour. Do we know how to change that? Anybody got an idea?
Roughly 2.2 to 1.
Yeah, but you got to memorize that. We need to do something for that. Okay, so here we go. So the thing I was taught as a child in like 3rd grade was speed of light is 186,000 miles per second. Woo! So I know that number. I did memorize that one early on. And the other thing you have to know is you have to change seconds to hours, and that's there's 60 seconds in every minute and 60 minutes in every hour, and 6 times 6 is 36, and there's the 2 zeros. So if you do that numeric out, then it comes out to 67 miles per hour. Aha! I know that. That's a car speed.
Hey, Mary
By the
Lou.
way, that's 1/10 of the speed of sound.
It is that. So it's not real fast as far as sound goes. We could shout better than that, couldn't we?
10 times as fast.
So, Mary Lou.
I think this is intriguing because I could drive my car that speed. Woohoo! You can't hardly do that ever in science. It's all really fast generally. But anyway, Ron,
So help me out here a little bit. When we're talking 67 miles an hour, we're not talking about the lower level of the ionosphere and how much it's dropping or rising. We're talking about the speed of the Doppler shift in relation to the frequency, or am I going totally the wrong way and everybody's laughing at me?
we're not laughing at you because you've got the real question. So for the scientific method, we had a hypothesis that the eclipse would do something to the ionosphere. We took some measurements. We did some experiment. 15 people looked at 10 megahertz and they did an experiment. And this is what came out of it. And we have these numbers and we have this graph and everything. And we've calculated a speed. And now, how do we state this? What does this mean? What is this car or something, the car in the ionosphere, whatever, it's going along at 67 miles an hour or thereabouts. Is this a real velocity? And that's supposed to be or rather than of. I type funny sometimes, sorry. Or is it something else? Nick,
Isn't
Nick
isn't
knows
it
the sort of stuff. What do you think, Nick?
Well, I think it's the layer, you know, if we're thinking of the ionospheric layer as being something that's reflecting the signal, then reflecting is the wrong word. Then the thing is that, you know, like the actual ionosphere itself, the reflecting surface has moved during that time period and then moved back down again. That was my interpretation.
Okay. What is really moving?
Well, the reflecting, yeah, again, you know, we're bouncing off something, and if that something is not stable, then something's going to happen to whatever's being bounced off. If you get me.
Yes, and you're being
you know,
you're being totally vague here. Has anybody else got an
um,
idea of how to really say it? Nick is saying it right, but he's not saying enough.
What's changing is the path length.
Yes. Now we're getting closer to it. Good job, David.
Is it the total electron content? We're looking at that. Is that what kind of helps to form that lower layer of the ionosphere? Folks, you all know I am the non-scientist, so I hope I'm not sounding way off on this, but I'm wondering if it's related to that.
It is related to that, and you got it just right, Ron. You shouldn't be shy of that. So I think this is a really funny measurement. I just like to churn it over in my head. There is nothing really moving. There are no atoms in the ionosphere which are zipping upwards or zipping downwards at 67 miles an hour. Although at first, so you interpret the directions upside down from the graph. The dip low says that the ionosphere reflection point is somehow moving upwards away from us at 67 miles an hour. And then it stops, stays at 0 for a split second, and then it moves back down toward us, toward the Earth's surface, at again 67 miles an hour. But yet nothing is really moving. It's all done with smoke and mirrors. This is a mirror thing. This is the reflection point and the path length between people who are doing
and it's not moving at that speed because this is an oblique path.
Yes, there is a bit of obliqueness going in there too. But this is the right order of magnitude. I mean, it's not going at 5 miles an hour, neither is it going 1,000 miles an hour. It's going something in the 50, 60-ish sort of thing. Any rate, I think this is a very interesting question, but let's move on. Yes, Nick?
Yeah, I'm sorry. Are you saying then that the reflective point is not moving?
The reflective point is moving, but it's not. It's not any physical.
That's what I said too.
Yes.
Maybe vaguely, but that's
you
what
made it sound like there was something physical moving. There's nothing physical moving. It's just they're stopping being ionized, and then they are being ionized.
But the reflective point is moving. You know, I'm not saying that there's a mirror there. I'm saying that the reflective point is moving, and
the reflective point is moving, and there
as
is
Dave
no
said,
mirror.
the path length has enlarged and then shrunk again.
Yes, And there
But
isn't
what
a mirror
actually-
that is actually moving.
But what
It's
actually
weird.
is moving is the electron density, which causes the refraction, is moving up and down due to ionization changes, which
Yes,
is
that's
giving
very, very
rise
good.
to the Doppler shift.
But it's
But
not
the
that
ionization isn't moving, it's just
No.
changing.
It's changing,
changing but not moving.
right? So the
Yep.
reflection point moves. Because the
Yeah,
density.
But it's We
So,
need
so interesting. If I'm understanding all of you right, I kind of had it a little bit earlier. So we're talking about the state of matter, or the state of the electrons or the atoms, or whatever term is appropriate. What we're talking about, their state is,
Yes.
is changing then, but not necessarily their physical location. And is that
right.
Exactly right.
And yet it comes across in these measures as a velocity. Moving right along. We'll think about that later. So now I wanted to start you on a very short experiment here. And this took way too much longer than I thought it would. I'm sorry. But at any rate, so the experiment is you draw a straight line, horizontal line across a piece of paper. You place a toothpick vertically down from that line, another one below it, and draw a second line there. So here's my piece of paper. You see there's piece of paper, two lines on it, and the distance between these lines is 1, 2 toothpicks. If you have a short pencil, you do it 2 short pencils line. If you have a large paper clip, you do it 2 paper clips long. But it's important that the lines be separated by twice whatever it is you're going to drop on them. So the way to do this experiment, I will expect some numbers from you guys next week. So what I do is I have 5 toothpicks in my fingers here. Can you see the 5 toothpicks? And I put the paper on the table and I drop them onto the paper. Okay. I drop them all at once. If one of them falls outside the paper, you pick it up and do it again. It has to fall on the paper. Then you count the number of toothpicks which touch one of the 2 drawn lines. And you write that down. You pick it up and repeat it again. And then you make a little table that has 3 rows in it. First row is the total number of toothpicks dropped. So the first thing is going to be a 5. And then I'm going to do it again. And altogether, then it will be 10. And then I do it again and be altogether now 15 have been dropped. And then altogether 20 have been dropped. You can do this as well. Then you have the second line, which is the total number of toothpicks that have touched a line. So when I did it with 5 of them, only 1 touched the line. And then when I did it with 10 of them, 2 more touched the line. So altogether, I now had 3 had touched the line. And you just do that. So you have only four boxes to fill in. Okay, then. Oh, we have to go back. Hang on. Then you have a third line in your table, which is the ratio of the numbers that you dropped divided by the numbers that touched a line. So it's 5 divided by something or other, and 10 divided by something or other, and 15 divided by something or other. Okay? Do this experiment. It'll take you 10 hours to do this. This is really tough homework, whatever. And so the homework for next week is to do the experiment and to guess what the toothpicks are telling us about the universe. Okay? The second part of the homework is read the quotes about the scientific method, which I will show you momentarily. Choose only one of the quotes and write a sentence about it. I want people to write stuff down. Don't look at me like that. And then the last question is, what particular hobby, sport, or experience has taught you about the physical world? One of my grandsons is now playing baseball. He's learned a lot about the physical world, about trying to aim the bat at that ball which is coming speeding toward him. But at any rate, okay? So here's the quotes. We're going to send them to you separately. I like number 3 by Mark Twain. First, get your facts, then you can distort them at your leisure. All right, we will send them to you. Okay, see you next week. But maybe Gary has something to say, right?
So you're
No, that
going to
was,
send an email.
yeah, I'll append it onto our meeting announcement in Google Groups.
But they're fun. So anyway.
That's fantastic, Mary Lou. Thank you very much for putting that together for us and looking forward to next week.
You never know.
Could you put those quotes back up for a second?
Yes,
Well, can you send them in an email?
we will do that too. Hey, look who's here.
And
Did the
not
Hayes
for
family
next
win their?
week's announcement. Before that.
Yes, you should send it right away.
It was, yes, everything worked out very well today.
Good. So Nathaniel, do you know about these quotes?
Not too, no, I don't.
Okay, I really like number 4 because Harlow Shapley was an astronomer. So these are all about the scientific method, which is the interplay between theories and data, theories and experiments. And I like.
You missed one, Mary Lou. Charlie Chan.
Oh, we could add that too.
Theory like mist on glasses. Obscure facts.
Oh, send me that one. No, type it out and put it on this thing. Charlie Chan?
Yep.
Mist on the glasses. Yep. So I like number 4. A theory is precise, clear, and believed by no one except the person who wrote it. On the other hand, experimental measurements are unclear, messy, and believed by everyone except the person who actually did them. We're going to talk about these next week, and you should have something to say about just one of them, something like that. Okay, Gary, anything more to say?
No, not at all. I think that's wonderful. Is there anything else anybody wants to cover yet this week? Otherwise, we'll bring it to a close. Well, good. I hope you all consider yourself sufficiently educated for a short period of time.
Did you have fun?
Yes.
I did.
Definitely.
I got my toothpicks and I'm ready to move on. So
Yeah, you got to do the toothpick one. It's really cool.
I wrote that one in the
have you done the
Mary Lou.
toothpick one with your grandkids, Mary Lou?
Not yet.
I'll have to see if Anthony will be patient enough to try it.
He probably could. With a 2-year-old, we can't do a lot of stuff. But anyway.
Nathaniel, any comments you want to make before we close today?
Did people get to see the figure of the solar eclipse QSO party RBN WhisperNet PSK results?
No, where would we see that?
2 sec, I'll share.
I can show it. Let me get it handy.
Yeah, Mary Lou, you might have to stop sharing on your end. There you go.
Great. So Bill Engelke made this plot using all the WhisperNet PSK reporter and RBN data. Using the code I originally made for visualizing it, but this is April 8th, 2024. This is 10 meters, 15 meters, 20 meters, 40 meters, 80 meters, 160 meters, all over the United States. This is 24 hours worth of data. So this is 0 UTC, midnight April 8th. This is midnight April 9th UTC. Right here, you can see that little bump there. That's the eclipse in the ham radio data. There's actually a little bit of an enhancement here, and there's a little bit of a cutout there. And that is all the eclipse. So the D region absorption went away during the eclipse, and the 7, 3.5, 1.8 megahertz bands, they clearly opened up, and we can see it beautifully in these plots that have over 52.7 million data points in them.
Where can we see that at, Nathaniel?
I can email it out. I can email it out to the listserv.
Yes, can't you put it right away on the hamsci.org page?
Yeah, with a quick summary would be really helpful.
Great. Yes.
I'll just find it there. Thank
Okay.
you.
Yeah. We'll get that up there. But Bill Engelke sent this to me the other night, and I think it's just absolutely amazing.
Pretty cool.
I'm also amazed at how quickly he was able to turn that around. I mean,
Yeah.
obviously you've done a lot of work on this in 2017, but it just shows how from one event to another, you can build on previous experience and move along rather quickly.
Well, there's a lot of work that's been going on this one project that Bill and Mary Lou and I are on. And in that particular project, we have a team that meets every Tuesday morning. And in that particular project, there's a funded effort to actually aggregate all the PSK, WhisperNet, and RBN data into a single database. And we're working on getting that posted to the Madrigal database, which is run by MIT Haystack. And that's a database that's used by scientists for science. And in that process, we have developed a standard form for visualizing making summary plots of this data on a daily basis. So we're getting ready to roll that out. And so this is one of the products that came out of that, that effort. And actually, I'm really thrilled with it because, in 2017, when we first, as soon as the SEQP was done, it took me a long time to figure out how to plot the data in such a way to actually see the eclipse effects. And it took a long time and it was very stressful. And, this time, having this software ready to go and having it in this format and just to have it come out so clearly, without really doing any additional work is just fantastic. Because I think there's more work that can be done that's going to bring out more information than we see here. But just to have this kind of like big picture, have it show up in the big picture plot like this right away is just wonderful. I think Mary Lou wanted to say something.
I have a question about the lowest one there at the lowest frequency. There's the mountain, which is the eclipse, and there's a little cloud hanging off to the upper right. What's that?
Yeah, someone asked me about that cloud, and I don't know.
Okay, to be determined.
To be determined.
Yep. Okay.
Yeah, that's a really good question. I don't know exactly what the cloud is.
See, he can say I don't know. We can all say that.
Yes. So do you think when I post this on the website, should I put a little box around this? Red box around that section?
I wouldn't label it Eclipse so people know what it is.
Yeah, or maybe the middle of the three, the one next up, the three.
Here, I can mock this up really quickly. That way I can get
Is that your
this.
house, Nathaniel?
This is what Adobe Firefly thinks my house should look like.
Yes.
My house isn't that far off from that, actually. Okay, so let me grab that. Where did that image go? Stick it over here. Because maybe I can just get a quick blurb up on the HamSci website really fast.
Good idea, Cam.
To get it out there. All right, so there is the figure. All right, so we can annotate.
Yeah, send me that one too, Ron.
Text fill, no fill. Wait, I need shape format. I need shape fill, no fill, shape outline, make it red. And wait, thicker. You think I should put some arrows there?
No, that's good enough.
That's good enough.
Maybe a word in red that says eclipse.
Great. So we're going to insert a text box for Eclipse. And I will How does that look?
Perfect.
All right. And then
Could you put the word total before solar? That's
Oh, it isn't total everywhere.
it wasn't total everywhere, it's partial some places.
well, that's true, but this was considered a total solar eclipse rather than annular.
Or you could just put the date.
Well,
No,
that's the date's on there.
no, solar eclipse is good. Yeah, there you go.
All right. Oh, okay, so let's try save as a picture. Yeah, we can just get this blurb up there really. Let's see. Let's see, 2024 0408 SEQP first results. Save that as a PNG.
Did we put this on social media? Do you think that would be a good idea?
I think so. Let me get on the website first. And then we can
Will it affect the publishability?
no.
Okay. Just
It's not reviewed.
Mary Lou, while he's doing that, I put on one of my favorite quotes about scientific experiments from Isaac Asimov, just for your grinning pleasure.
Yes, I like Isaac Asimov.
Yeah, this has been quoted in different ways, but this is the actual quote that he made on it. So I've always gotten a kick out of it.
So read it out to people.
Okay. Isaac Asimov, most of you know, one of my favorite science fiction authors, and you know of him with the Foundation series and stuff from the 50s and 60s. Famous biochemist said, the most exciting phrase to hear in science, the one that heralds the most discoveries, is not Eureka, I found it, but that's funny.
Yes, that's funny.
Solar eclipse.
Ron, do you know what his son does for a living? Eric Asimov.
I read it some years ago. Didn't he have both a daughter and a son? But no, I don't remember what his son does.
Yeah, so I read his son's column every Wednesday in the New York Times. He's the wine editor.
Oh, really? How interesting. I know Isaac Asimov was a professor at a college back east. I don't remember which one, in biochemistry and things like that. And
Mostly he was a writer.
yeah, well, they got on him a little bit because he was spending so much time on writing. And then when he became so popular in writing nonfiction and fiction, they backed off and gave him some leeway and cut down his class load to keep him on the faculty there.
Did you ever hear him speak?
I have seen some of his talks. I did not do it in person. When he was in his most popular time, I was in junior high and high school and an avid reader of him and Heinlein and Clark and many of the others. Very interesting speaker, though, very engaging.
Yes, and I heard him in person several times. He was an amazing speaker. I don't know how he would do it, but he could answer questions in paragraph form with subsequent clauses and whatnot, and you could just see the commas and the punctuation going along too. He could just speak things, and he said he did that with writing. He hardly ever edited. He just wrote books.
Yeah,
Go back and edit them. Just
yeah, he said that he normally spoke his books before he wrote them down. He would get the reel-to-reel cassette or the reel-to-reel tape recorders and start talking into it. And that's how he did something like 90% of his quote-unquote writing was he would say it verbally, then go back and listen to it and write it or hire somebody to write it up for his different papers and books and stuff. So sorry, I didn't mean to take away from what Nathaniel's doing. So
think Nathaniel's being busy here.
Yeah, we don't have any of the Jeopardy music going, so they had to put up with me and Mary Lou in place of it.
Yeah, we're talking about stuff. Yeah, I liked his rating as well.
Let's see, that is a very big thing. Can I make it smaller for the thumbnail? Let's see. Okay, what do I have written so far? I have the April 8th, 2024 Hampside Solar Eclipse QSO party. Let's link this to slash eclipse over 52.7 were observed in the United States using PSK reporter. There's the map display. WhisperNet. And reverse beacon networks.
Nathaniel, check the URL on WhisperNet. You have whisper.rocks.
Yeah, I know.
Okay. Separate sites.
I know. I think Rob Robinette has been preferring whisper.rocks for getting the data. So okay. Let's see. Eclipse effects were observed between 18 to 21 UTC, particularly on the 1.8, 3.5, and 7 megahertz bands. These bands all showed enhancements in propagation resulting from the eclipse, suggestive of a reduction in D region absorption. The 14, 21, and 28 megahertz bands also showed hints of eclipse impacts. A reduction in near ranges during the eclipse, a reduction in communications observed at near ranges during the eclipse
Misspelled
suggests
ranges.
near ranges during the eclipse suggests the likely results from a reduction in ionospheric electron densities during this time. More analysis to be done in the future. Do you think that's sufficient?
Good job.
Yep.
Okay,
Yep.
great. It'll get it out there. All right, let me make the thumbnail a little bit smaller. Copy paste. Open. Let's see, is there a reduce crop adjustment, save options? Do they have a scale here? That's a view. Do I have open with GIMP? Because for the thumbnail image, I don't need it to be full size. Okay. Image, scale image. 200 by 176. Make it 400. Scale. %. That's good enough for the website thumbnail, I think.
And Nathaniel, we're okay to include that in our presentations, correct? As long as we give acknowledgement.
Yes, that would be fine.
Okay, just wanted to double check.
Okay. Special thanks to all the team members. Hey, JP.
Are you going down to that thing?
Yes, I am. I know. One
Mind if I
second.
walk down with you?
Please do. Volunteers, team members, and volunteers who made this possible. This work was supported by the National Science Foundation and NASA. Great. But yeah, National Science Foundation and NASA, and led by the Scranton. I think that's. I think I'll just put it right there for now, because I'm gonna leave out other people. Bill Engelke did a lot of work on this at Alabama.
Mm.
You know, a lot of people. All right, let's preview this. What's that?
Cool.
Okay, great. Let's get this on the front page here. Save. There it is. How's that look?
Great.
Yeah, beautiful.
Wonderful.
That's awesome.
We did it. Yay.
Mackenzie, we've got a post for Facebook and everything else.
Yep.
Thank you, everyone.
Thank you. See you
Thank
next
Good night.
week.
Good night, everybody.
Take
Have
care.
a great week.
Merry Christmas.
7 threes.
7-3.
I'm
Okay, thank you.